Hey everyone, and welcome. Today, we're tackling a fun problem called max difference you can get from changing an integer. The goal is to take a number, transform it twice to get a huge number and a tiny number, and then find their difference. We'll break it down step by step. It's less about complex math and more about clever logic. Alright, let's look at the rules. We start with a number. We get to perform an operation on it 2 separate times. The operation is, pick a digit in the number, let's call it x', and pick another digit, y'. Then, you replace every single occurrence of x with y'. We do this once to create a number a, and a second time, starting from the original number again, to create a number b. The final answer is the difference between a and b. A key rule is that the resulting numbers can't have leading zeros unless the number itself is 0. Let's take the number 555. Our goal is to make the difference between our two new numbers, a and b, as big as possible. This means we want to make a as large as we can, and b as small as we can, to make the number huge. What's the best digit to use? A9. So we can pick the digit 5 and replace all of them with 9s. This turns 555 into 999. That's our a. Now, for the smallest number. What's the smallest digit we can use? Usually it's 0. But the rules say no leading zeros, so the next best thing is a 1. We can replace all the 5s with 1s, turning it into 111. That's our b. The difference is 999 minus 111, which is 888. Simple enough, right? The trick is figuring out a general strategy. What's a reliable way to always get the biggest number? Let's think greedily. To make a number bigger, we want to change a digit to a 9. But which digit should we change? Changing a digit on the left side, like in the hundreds or thousands place, has a much bigger effect than changing one on the right side. So the best strategy is to find the very first digit from the left that isn't already a 9, and change all instances of that digit to a 9. For example, with 1231, the first digit is a 1. It's not a 9, so we'll target it. We replace all the 1s with 9s. The number becomes 9239. That's the biggest we can make it. Now for the minimum number. This one has a couple of tricky parts. The simplest case is when the first digit is not a 1. To make the number as small as possible, we should change that most important first digit. The smallest we can make it is a 1, because of the no leading zero rule. So we replace all occurrences of that first digit with 1s, like our 555 example becoming 111. But what if the first digit is already a 1? Like in 1010, we can't change the 1 to a 1, that does nothing. And we can't change it to a 0, so we have to leave the first digit alone. Our next best move is to find the next digit from the left that we can change to a 0 to make the number smaller. We skip any 1s or 0s we find and grab the first digit that isn't one of those. In 1010, the first digit we can change is that second one. We replace all instances of it with 0, and our number becomes 1000. This is the key insight for finding the minimum. Okay, here's the complete Python code that puts those ideas together. Don't worry if it looks like a lot at first glance. We're just going to walk through each part, and you'll see it's just implementing the greedy logic we just discussed. We'll start with how it finds the maximum value, a. First, to find our maximum number, which we call a, we start by converting the input number into a string. This makes it much easier to look at individual digits. We then loop through the digits of the string from left to right. The moment we find a digit that is not a 9, we've found our target. We use a replace function to swap every single instance of that target digit with a 9. Then we use break to stop the loop immediately, because we only ever want to act on the very first non-9 digit we find. Now for the minimum number, b. We first check the very first digit of our number string. If that digit is not a 1, we're in the easy case. We simply replace all occurrences of that first digit with the digit 1. This immediately gives us the smallest possible number we can make. But if the first digit is a 1, we go into our second case. Here we have to search for a different digit to change. We loop through the string again, but this time we start from the second character. We're looking for the first digit that is not a 0 and not a 1. As soon as we find it, that's our target. We replace all instances of that digit with a 0. And again, we break out of the loop because we only care about the first opportunity we find. If we go through the whole number and don't find such a digit, like in the number 101, then no change is made, which is the correct behavior. So how efficient is this greedy approach? It's really fast. For time complexity, everything we do depends on the number of digits in our input number. Let's call the number of digits dcams. We scan the string a couple of times, And the replace operation also takes time proportional to the length of the string. So the overall time is on the order of dchems. Since the number of digits is related to the logarithm of the number, you can think of this as big O of log n. For space, we need to store the number as a string, which also takes up space proportional to the number of digits, dx. So the space complexity is also order dx. This is a very efficient solution. So to wrap it all up, the key to this problem is to think greedily. To get the biggest difference, you need the absolute largest number and the absolute smallest number you can legally make. For the maximum, the strategy is simple. Find the most significant digit that isn't a 9 and change all its copies to 9. For the minimum, you have to be mindful of that leading zero rule. This creates two distinct cases. If the first digit isn't a 1, you change it to a 1. If it is a 1, you have to hunt for the next possible digit you can change to a 0. By following these simple greedy rules, we can find the answer efficiently every time. And that's it. Hopefully that breakdown made sense and the logic is clear. If this video helped you out, I'd really appreciate it if you hit the like button or subscribe for more problem-solving guides. If you have any questions or a different way to solve it, drop a comment below. Keep up the great work, keep coding, and I'll see you in the next one.